Hi again. It's 36 minutes past midnight, so we have teaching within the next few hours when it's daytime again. So yeah, I'm a little late, but today's lecture will be data linearization and multilinear regression, as you can see. And then you have fall vacation. Let's start with this. I found it in a nice little PowerPoint here. And the problem is that there is some data which is just doesn't fit a linear relationship like this. I know you have played with polynomials regression, and there you can probably fit a second order polynomial or something here. But that's not always enough, and if you have a physical relationship you can describe, you will probably prefer that equation. And here's an example of an exponential equation, and you can see that is not really linear. But a way to do it, if we take the natural logarithm, you can see suddenly the line is straight. And why is that the case? Here you can see what you do. You have a relationship here, and what you do when you take the logarithm, you can kind of split it out, so you get a relationship. You can recognize here you have b, which is the intercept. That will be this one, showing here. And then you have a rate, t, and that will be the slope you can see in this one. So now you have a really nice linear relationship, and you can kind of extract the parameters from a plot if you have some data. We'll have a look at that later. So you can see what happens here. That's kind of what I said. You end up with this. So if you want P0 for the final equation, you need to what's that called? I can't remember in English, but you can see what it is here. It's too late for doing this stuff. And then if you have a power function, like for example the flow over a weir, I don't know if you know what that means. I think it's you know, if you have a stream, you can kind of block the stream, and then there will be a flow over this dam. What you can do there is, again, you take the logarithm and the logarithm to this one, and what happens then? You have a nice linear relationship. That's just calculating, you know, when you take the logarithm. I don't know why it's not the natural logarithm, but you might as well have used that one. But then you get the logarithm of c here, and the slope here directly. And that's what is said here. As I'll say again, you can download this one, and then you have time to read it yourself from the blackboard. So here you can see how you estimate b and c. And the nice thing is here you don't have to transform m or a you have here. You can read it directly from the graph from here. If you have a saturation growth rate equation, it's kind of the same little trick you do. But the problem here is that you need to know the maximum growth rate in order to get it exact, but you can have a guess, and then you can fit it anyway to this equation here. Here's a kind of overview of different equations. and how the constants have an impact. You have this power function, and depending on here you can see it's a half, so it looks like this. If you have a negative, it's the other way around, it's the direction. So it's all different function, and keep notice this one. This one is quite often used in biology, and if you inverse that one, playing a little with these constants, you will have to do that in an assignment, then it will have the same shape as your MIBK data. Here's some example of the function, nonlinear function, what you do to linearize it, and what you have to plot. Then here you have to transform x by inversing it before you plot it. At this one, you have to plot x multiplied with y in order to get this. And when you have that, you can get, by looking at the slope, you get this one, and then you get the intercept, which will be d divided with c, and so on. And here's the one you have to have a closer look at in the assignment. Else, read it yourself. And if you want to see how it's done with some examples, there's a nice little screencast here. Let's have a look. In Vimeo. Let's scroll down. The link is quite short up here, so you can type it yourself. And they have a lot of nice screencasts from the University of Colorado Boulder.
We divide both sides by x. So now we have sine.
You'll have to look at that screencast yourself, again, because it's a little late. So let's go back. And take this one, you'll recall this planet data. And that was this relation by Kepler, or power function. And if you transform that, you can see you have to plot the natural logarithm of y and the natural logarithm versus the natural logarithm of x. And by doing that, you can extract here the slope and the intercept. And then of course you have to transform that in order to get this expression. You can get this one directly, but you have to play a little here because you need to transform it. The inaccuracy of the parameter will of course change when you transform it like this. And that is when you have a little change and you play a little around here, then you can see you end up with a little change of c is equal to this. So what you do is you put in the inaccuracy, where do we have it? Here. And you multiply it with the location where you are, and you get this. So now you transform the inaccuracy to this, and that is the final function with Kepler. You can go back and look at some of the former assignments you had. So here is first assignment you have to do. You have to transform, do a transformation to linearize the MIBK data. And there, as you saw, there was this biological degradation process. If you go back in this notebook or in this screencast, and that one you have to use to fit this, to do the transformation, find the best parameters using linear regression. And when you've done that, then you have to transform it back as we did in the former examples, or as you saw. Of course, there is some cases where some of the points won't fit quite well, so you have to play a little bit and discharge some. And then, I'm not sure if this can be done, we are working on that still, so you'll know that tomorrow. But then you can try to optimize this number, I think it's L, you have to set by visual inspection. That's the maximum rate or the initial level at the MIBK data. When you've done that, then you should have a go with the nonlinear model fit using Mathemathica. There you don't have to linearize it. It's kind of the same as a linear model fit, but there is a small difference. You can see all this in help. As it say, the nonlinear fit produce a nonlinear model of the form under the assumption that the original data are independent. And this is important and normally distributed with a mean and a common standard deviation. And this is something you need to verify when you get the results, that this is fulfilled. I think I'll come back to that in the next lecture. There is a nice example I found. But here at how it works, the linear model fit is exactly the same, except for here where you put x, and what you used until now is x and x squared and x cubic if you have a polynomial. But here what you do is you write the whole model, and then you kind of say that these are the parameters it's supposed to optimize, A and B, and it's X, which is the variable with the data. And then you end up with the model here, and you can do all the things you're used to. This is just a direct extract from the help menu. You can plot the data, you can get the residuals, plot that, and so on. So look and help to get further information on this one in order to solve the next assignment, where you have to do exactly the same here, but you just put in the function you found you had to linearize, and then you ask it to find the parameters directly. And here you don't have to exclude any data, and it will find L, which is missing one here. And then try to compare the result and the residuals with what you got in assignment 15 and 16. I think it's 16 which is the most important, where you end up with a fourth order polynomial or fifth. And try to compare these. So, multiple regression. There's an example here from the former lecture notes. I just copied directly. But the idea is you have a function where you have y, and then you have some independent parameters, x1, x2, x to xn. So you get this expression. And you can probably recognize that when we had the polynomial fit. There, this one would be x, this one would be x squared, and so on. So what you have is you have the y here, and then you have the independent variable, and you have the independent variables here. So if you consider this as the first one, this one as the second, consider that, for example, this, if you should have a, what's it called, a parallel or something to remember on, it's kind of the same as a polynomial regression. Instead of x squared, this is just some independent numbers, x2 and x3. So, if you try to put in these data just to have a fast go, this is just to have it look nice. Here's an example of the data, where you have y, and you have x1, 2, 3. And then you have the function you get here when you just run it. Let's have a look. It's this one. So what we have, you know, this print, you just have to look at this. We have the data which is equal to this. I just entered manually, put some headings on. And then when we have the data here, that's important, this here. You can see you have the linear model fit data, that's what you are used to. And then you have x1, 2, 3. And if you really wanted some interaction, if you expected that this one and this one are not, they depend on each other, then you could have added that like as this x2 multiplied with x3, like this. Then you added that component to the model, but more of that in the next lecture. So running this, you will get, let's close it again, this. And then of course you can do as you're used to, you can run the ANOVA table, where you can see if the variables are of any significance, which they all are here. You can get the parameter table, the parameters, you can get the parameter table, the confidence interval and all that stuff. So that's exactly the same as when you did the polynomial fit. But now it's multiple linear regression, so you have in fact been doing that for quite a while, but now it's independent parameters. There's an example here I used from the former lecture notes, where you have the rate law for the catalytic gas phase reaction, and you know, I'm not a chemist, so I cannot tell you so much about this. But it can be complicated to linearize it and find the parameters. And here is an example. Looks very complex when you look at it, and you have to play with it and work with it. But if you inverse this one, you can see, and you divide it, then you end up with this relation. And now it seems easier to handle it. If you then take the square root, you will end up with this relation. So now you can see, if you have this as y, this transformation, you have b, or the intercept, and then you have PA and PB. So now you're kind of able to plot it in, it's not 2D, it's a kind of 3D, because you have two axes here, you have x and y, and then you have z here, if you should try to look at it. Now it's multiple regression. It could have been 10, so it's kind of 10 dimension instead, if that was necessary. So we have linearized it here, has kind of set it here. You have y, x, and x2. You end up with these parameters. And when you look at it here, and I don't have the plot, it's kind of a nice fit. However, if you're a chemist, you have probably noticed there's something wrong here. This one is negative. And that is not good. So it doesn't make sense. It's a nice model, but it doesn't make sense. So you need to use your common sense, because this equilibrium constants for these are defined like this. I think there's missing a sign here. So that must be positive. So what is wrong? The problem is, when you look at this data, they are not independent. You can see this, it's always 1, the sum. So in fact you only have one independent variable, call it PA, because you can describe PB using PA. So you can, if you swap that and you end up with this one, then you get these results, and that's a good fit. And it's more healthy. The last assignment here is optional. You don't have to do it, but it's really a good training. And for you, your chemist, you will probably understand this better than I do. But this one, you assume that's the rate limiting one. And you can describe the rate by this equation. The data you have, you can import. It will be put together with the this notebook or the assignment, and you can see I imported here. A fast way to do it, if I should give you a little trick, is if you write import. See, we have it here, very long one. If you take this one, insert, and then say file path, then you can find your file and you just double click it and it has inserted this link for you, and then you can start to work on it. Let's see, home. Then I have table form. You don't have to look at that. I have to flatten the data because it looks a little, I don't know if, I think I have it here. This is how it looks in Excel. And it's, because this is put like this, it's being a little messy, so you need to flatten it, because you get too many, what's that called? These ones. Curly brackets, I think it's called. So that's why I need to flatten it in order to make it behave, and then I make the headings. But that's it. Then I have the data, and I can, or you will have the data, and you can start to play with it. And here's your assignment. So you have to try to linearize it. This one, it is possible. Then use a linear fit model to get the parameters, and then try to do it directly by using nonlinear fit model. And you have to look at that you can put constraints on. So where you got the negative values, you can put constraints on saying that this value must be bigger than 1 and smaller than something. So in that way you can constrain the nonlinear model fit. But you can find that in help, and then try to compare the two. I think this was it. Yes, I hope it was not too confusing. See you not tomorrow, but later today.